can't really acknowledge everybody today. There's so many people gone. So if you want to say hi to somebody, you can raise your hand and say hi to that person. Anybody want to say hi to somebody? Okay. Breesley?
Hi, Kaylee. Hi, Ella.
That was Maddie.
Swim fast, Wongsness.
Oh, Luke, swim fast. Kendall wants to give a shout out.
Hi, Whitney.
Whitney, we do feel bad for you. We hope you're better at some point here.
Hi, Hannah, Hattie, and Whitney.
Oh, wow. Alyssa feels alone.
Hi, Mom.
Okay. If your mom watches our calculus videos, wowzers. Okay. Here we go. Today we're going to do something really cool. Today we're not going to find area, we're going to find volume. And it is kind of ridiculous how we go about this process. And it's kind of like this. Suppose you have a function, and you bound that function from A to B. And then you take that function and you revolve it around the x-axis. So I have this kind of weird shape going on right here. What I'm going to do is I'm going to take this solid block and I'm going to rotate it all the way around. So if I rotate it all the way around, I'm going to do my best to draw this. You might get that on the bottom side, right? And you're going to have this three-dimensional shape that evolves. Anybody see like a vase that's sitting sideways? Oh. Okay, we got the Amber Alert going off right now. We hope that the child is found. We do hope. So do you see a sideways vase? Yeah, the difference is that the vase is not hollow, it's solid all throughout. And the nice thing is that if you were to take this vase and you were to slice off the end of it, okay, just slice off the end of it, what shape would you get if you were to slice off the end? You're going to get a circle, a really thin circle, aren't you? In fact, we're going to call it a disc. No, because I'm drawing a three-dimensional shape on a two-dimensional surface, it does kind of look like a football right now, but if you think of it being revolved around, it's going to have the same distance here as it does there. So this is definitely a disc. And so the cool thing is we can find the area of a disc. We can find the volume of this disc. Almost think of it like a quarter. Like a quarter has got like, little bit of width to it, right? Does this have horizontal width or vertical width? Horizontal width, so the width is dx. So if I want to find the volume of this one slice at the end, I take dx times the area. This makes the shape of a circle. What's the formula for area of a circle? Pi r squared. Now what's interesting is that this piece right here is the radius. Can somebody tell me how to rewrite r so that it has an x in it? What is something up here that defines the radius? It's the function. Whatever the height of the function is, that's your radius. So it turns out that you have pi times f of x squared. And that's the volume of one of those things. We don't want one of these disks. We want how many? We want an infinite number of these disks sitting all throughout here. And so we slap on the integral sign from a to b. You can put the pi wherever you want. No. Nope. We did it last unit too. Doesn't matter. All right. So let's try one of the most basic examples. So the first thing you're going to have to do on your test is you're going to have to be able to produce area between two curves. The second thing you're going to have to do is be able to produce volume by using disks. So let's represent this area. We're going to do y equals the square root of x. What does that look like? So I've got the piece. I'm going to bound it from what to what? 0 to 4. Does everybody see that this is the area that I'm working with? We're going to revolve that around the x-axis. Some people ask, do they have to draw it? Not necessarily. I think it's helpful to try to draw what it looks like. So if I revolve it around, I'm going to get this kind of shape. Anybody want to suggest what that would kind of look like? That three-dimensional shape? I think of it like a ham.
I think it's like an eyeball.
Maybe like a half of a ham.
Yeah.
See what I'm saying?
I see what like an eyeball though.
Okay, an eyeball. I was thinking eyeball more like spherical.
Well, I mean eye as in like when you look kind of like look at a cross thing.
Okay, so if you cut the eye in half, I got you. I'm right there with you. Okay. Now, what's interesting here is as you look at this disc, as I slice it, I just look to slice it so I produce the same shape over and over again. And if I can find the volume of one of those slices, then I can find the volume of all of them put together. And so I'm trying to draw this to give you a visual representation of what's happening. It doesn't matter if you talk about the green slice or the blue slice or the red slice. Either way, when you slice it, you have a disc. What is the width of the disc? dx. The width of the disc is a horizontal width of dx. Okay? What is the height of the disc? Square root of x is the height. That is the radius of the disc. So when you look at pi r squared dx, our radius, we put in the square root of x for r. So pi times what? X dx. That is the volume of one disk. You would like to do an infinite number from 0 to 4. If dx is our width, then our bounds are x values, 0 to 4. And we integrate. Antiderivative of x. Pi times x squared over 2, evaluated at 4 and at 0. Plug in 4 and you get 16 pi over 2 or 8 pi. Which part?
That was just 4 pi. That was pi to the 3.
Are you okay with this? Okay. Are you okay with this? What's the antiderivative of x? And we evaluate it at 4 and at 0. You plug in 0, you get 0. You plug in 4, and you get 8 pi. So that would be about the most basic example you could see. Okay. Let's try one that's a little bit more challenging. Volume between x squared plus 1, x equals 0, and x equals 2 rotated around the x-axis. X squared plus 1. Thank you, Patty. I appreciate the sound. What is x equals 0? It's the y-axis, right? So x equals 0 is going to be this part right here, and then x equals 2, just 2 units over, right? Does everybody see the area that we're looking at? We're going to revolve that around the which axis? The x-axis. So it will produce that. Vertical lines. Yep, that defines the area. Those really end up being our bounds in the end. Yep. So I'm going to show you just a slightly different approach now. Remember how we talked about area being that rectangle? You could also think about drawing a rectangle that you would use to find the area. And then you're rotating that rectangle around. And it becomes a disc. You can even get a little bit of shading there to produce that color that you want. Anybody want to suggest what this shape will look like in a three-dimensional format? Can you compare it to something in real life? Okay, very good. I like the trumpet, but it's not hollow. I like the idea of a hat. I almost think of it as like a tree stump that's sideways. So all sorts of things you can think about. I noticed that throughout the years that some people have a very, very difficult time visualizing these things and understanding that piece. The spatial reasoning comes back to the geometry piece. I think spatial reasoning is something that a lot of people struggle with, no matter how good of a math student you are. Okay, so yeah, you're going to want to be able to see this. There are times where you're going to be given the shape on the AP exam so you can see what you're rotating. There will be times where it just tells you and you have to be able to produce the graph. So you want to be able to try to come up with it and understand, because we're going to look at different shapes on Monday. So let's start. I've got this. What's the width of these? Dx or dy? Dx. So dx times. What is the radius going to be? X squared plus 1. And I square that, I multiply it by pi. And what are my bounds of integration? 0 to 2. We do. Yeah, can somebody tell us, why did we square that? Yeah, because your volume is pi r squared dx. So you have to square your radius. Square your radius. Okay.
It's just a formula thing.
Sure. All right, so I have pi times the integral from 0 to 2 of, multiply it out for me. X to the 5th over 5. 2x to the 3rd over 3. Plus x.
Bounds of
If I plug in 0, I do get 0. But if we plug in 2, we get?
so you get 5.
32 over 5.
Oh, sorry.
Okay. 16 over 3. 2 over 1. We'll treat this as a problem without my calculator. Common denominator should be 15 pi times 96 over 15. 80 over 15. 30 over 15. 96 plus 80, I see that as 176, plus 300, I see as 206. No, it isn't. But what you should be able to see every once in a while, I got to stop and smell the roses, folks. You had no idea how to find a volume of that shape. For example, you were given volume formulas in geometry, correct? But you weren't given any volume formulas for that, were you? And so we used calculus to find the volume, and it doesn't matter anymore what shape we're given. Like literally, you can take any shape that you would ever be given in the world, you can find the volume using calculus. Now here's something that's interesting to hopefully interesting to somebody. Do you remember the volume for a sphere? It was 4/3 pi r cubed. We talked about that during our related rates unit. Somebody told you that once upon a time, but you never knew why that was a formula. Like when they told it to you in geometry, they couldn't do any reasoning. Obviously, with a triangle, it's easy. It's like we'll do a rectangle and divide it in half, right? But nobody was ever able to point to that and say, well, here's how we come up with that volume. You know why? Because in order to come up with that formula, you got to do calculus. This comes from revolving a circle around. And so we can prove all those formulas now. All right. Talk to your friend. What makes example 3 different? Talk. Go. Okay, 5, 4, 3, 2, 1. What do you got? Yeah, I would encourage you. A lot of times people get stuck on these equations. As opposed to getting stuck on those, focus about where it's revolved first, okay? And so as we look at where it's revolved first, it's revolved around that y-axis, and that is definitely going to change things for us. So what we want to be able to do right now, is we want to be able to draw that shape. What does 1/2 x plus 1 look like? Yeah, it's a line. So for every 2 I go over, I go up 1. So something like that. Are we okay with that? I'm going to bound it by that function, x equals 0. What is x equals 0? The y-axis. So I'll bound it there, and I'll bound it by y equals 3. What does y equals 3 look like? Yep, it's just like this. Okay? So it's bounded by those 3 pieces. So what shape does the area make? Makes a triangle. We're going to revolve that around the y-axis. So instead of drawing the same shape down here, I draw it up over here. Instead of drawing that vertical rectangle, because I'm revolving it around the y-axis, I will draw a horizontal rectangle. And that's what I'm rotating around. And I get that disc shape. Anybody want to take a shot at what this might look like in a real life scenario if we were to revolve this shape around? Yeah, it would be kind of a really flat cone, wouldn't it? Yeah, a really flat cone. That's a good analogy there. Okay. Okay. Sure, yeah, like the ones you use for spacers on the ground for like, yep, to mark. Yep. That's exactly what you're getting. Good job, Marissa. So again, your ability to kind of visualize that can help out. But I want you to look now. Look at my disc. Does it have horizontal width or vertical width? It now has vertical width. So now your volume is pi r squared dy. So that means that all of the variables used in the problem must have a y in it, whereas my function right now has x. So I can't have this as y equals with an x. I need it to have x equals with a y. What will you do to accomplish that? I have y minus 1 is equal to 1/2 x times by 2. 2y minus 2 is equal to x. You are 100% correct. This is my radius. I thought you said wait. Hooray! All right. Thank you for the enthusiasm. We're going to drop that right in there. Pi times 2y minus 2 quantity squared dy. Integrate. I need bounds. Please do not say it out loud for the whole class to hear, but talk quietly with the peer that sits next to you about what you think the bounds should be. Take about 40 seconds. Ready, set, go. So this piece right here, because you're revolving around the y-axis, we have to draw the because the revolution is horizontally, we draw the rectangle horizontally. Okay.
Will there be a vertical stretch when it's like the dx?
I'm trying to understand what you're saying. I'm struggling.
So you know how dy is when it's like a vertical stretch?
Vertical width. Yep.
So is that when it's like rotated around the y?
Yep. For a disk method, yes, all the time. Now, if your bound should be from 1 to 3, because it has y, it's a dy situation, or because it's dy, it involves y values for the bounds. So what you do is you just look at that original area that you drew, and you decide what are the y values for that parameter. Okay. Okay. Well, let's evaluate this. You guys know how to square that out. You're very smart. You got all A pluses in algebra. Actually, some of you guys have higher grades in calculus than you did in your college algebra class. Good for you. If I square that out, what do you get? 4y squared minus 8y plus 4. Good job, Patty.
Thanks, dude.
Let's take the antiderivative. Antiderivative of 4y squared. Whoop, I got to get rid of that integration symbol now. 4y cubed over 3 minus 4y squared plus 4y looks like it's going to be a really bad integration, but it really isn't. It's going to work out quite nicely here. Pi times, watch how this works out. What is 3 cubed? 27 divided by 3 times 4. 3 squared times 4. And 4 times 3. Great. I handled that, no problem. Now I will subtract 4/3 minus 4 plus 4, right? So what's great about this problem is noticing the things that cancel right away. What cancels? 36s are gone. 4s are gone. So you get 12, which is also known as 36/3. What is 36/3 minus 4/3? So 32 pi over 3. Folks, the integration is all old business. You already know how to do that. The deal is setting up the integral from the beginning, right? That's what we want to do. So, last problem. You guys are doing well. Good job. Got to keep good pace. We lost 4 days this month, right? 3? 3 days this month?
I'm
What's that?
too bad.
Yeah, no, it's all good. We all needed the break, right? But fortunately, we were all rested and ready to go then. So, I thought we had another snow day at some point, didn't we? Was that our 4th snow day that we had this year?
That one was January 9th.
Yeah, one in January. So, I guess we lost 3 days of the quarter. Okay. Find the volume of the area bounded between these curves. This is closer to what Easton referenced as the whole eyeball thing. Negative x squared plus 3x. When you graph that, if I factor out a negative x, I'm left with x minus 3. So you could tell that the x-intercepts are what? 0 and 3. So it goes from 0 to 3. Just a little parabola. And I'm going to bound it x equals 0 and x equals 3. So it's bounded right within where it passes the x-axis. Where am I rotating it? Over the x-axis. Yeah, Maddie's got it. It kind of looks like an egg. If I take one of those rectangles and revolve it, notice I get a disc. Now, right now you might be saying, well, Mr. Gans, I get it. We're always going to get a disc. No. On Monday, we're going to look at washers. Okay. Later on, we're going to revolve where you get cylindrical shells. And there's other things that you could get as well. I kind of look at it like a lemon. To me, it's got a lemon shape to it. Pi r squared, is it dx or dy? Dx. The radius is the distance from the x-axis to the function, which is negative x squared plus 3x. So pi times negative x squared plus 3x, quantity squared. That is the volume of one of those disks. We do an infinite number. We bound it from 0 to 3. Now, we're not going to finish the problem off because you already know how to do that, right? And on your test, I will ask you some problems where you will carry out the integration from the beginning to the end. You'll do all of this work. And in other problems, I will say, please do not evaluate, but just please set up an appropriate integral. And so we'll leave it there to model what we would do in that situation. Okay? Right, there really is no way. You just have to hopefully see it and set it up properly. Okay, take out your homework.